the object. That's what we're thinking about. The energy that I expend may be different, but that's the biological energy. Physical energy is something else. So these are the kinds of things I want you to be careful about. I want to do a few little things just to refresh you on the meaning of some of these words. For example, what do I say here? I'm going to roll a ball. Okay, so if I roll the ball, does it have force? No. There are forces acting on it because it stops. If I make a, so that's a very, this is getting to the idea of inertia. That the very key law that I'll emphasize later. The ball has velocity. Yes, no? Yes. Does it have acceleration? Yeah. Does it have mass? Does it have weight? Well, what's the difference between mass and weight? This is something that will come up periodically. The difference between mass and weight? Gravity is very important, right? One of my favorite jokes is if you want to go on a weight loss diet, if you want to lose weight, get in a spaceship and go into empty space. You lose weight, you'll have no weight. But you will have mass. Your fat cells will go with you. So your mass will be the same. The mass has to do with the number of particles in you. The number of neutrons, protons, and electrons. That's your mass. But that won't change if you go in a spaceship. On the other hand, the weight is the pull of the gravity on you. That's your weight. It's when you put yourself on a scale, gravity is pulling you down, pushes the scale down, and you read your weight. But in outer space, you wouldn't have anything pulling on you, so you will have no weight. So you want to understand those things. It's really nice knowing that. Makes you feel good. Momentum is a very specific property that we define. It has to do with mass times velocity, and it's often confused with energy. It's often confused with power because tomorrow somebody's going to say, Cal's football team has the momentum. Well, yes and no. I hope they have some, but it's a different momentum from what we're talking about here. They're playing with a lot of energy. Yeah, but that's not what energy has to do, and work have to do with the ability to make something move. And that's very specific meaning, very well defined. So I made a chart, which is also online, of what I think of sometimes on the street meaning of some of these words and the scientific meaning, very much more specific. And for example, you must really learn the physics meanings. So again, this is more propaganda. Well, what we're going to do is cover electricity from the very beginning, which may be very simple. But by the time we're through, you will potentially know how your cell phones work, why computers work as they do, all kinds of intricate things that electricity and magnetism do in our real world. Okay, so here's another outline. Of course, now here I think I'm doing you a favor because there are main ideas and subsidiary ideas. And it's a little hard as you as students to sort of sort out when the chapter headings, and section headings look all alike. What's the important idea and what's the secondary idea? Well, I try to outline it here for you. Broke it down. You've got to get the big ideas. And then the rest will follow. Sort of like geometry. You learn a few basic ideas and you can deduce the rest. And that's how I'd like you to learn it. Get the big ideas, namely, what is an electric charge? What is the force between the charges? What is an electric field of charge? And then the rest will follow. Time is fidgeting here. So, again, I want to emphasize, in a sense, the basic idea behind physics is that we have to look a little deeper into how things go and look for causes. For example, the fact that this chalk comes to a rest eventually. No, it isn't. Okay, inertia is working, but I don't know if I do it this way. Yeah, it runs pretty well too. Good. Okay, good. I'll slide out slower. Okay. Yeah, it comes to an end. Now, the thing I wanted to make, it's also a philosophical point, which is really good to know. See, in the old days, they would say, for example, the fact that this came to rest because they would say the natural state of things is rest. The natural state. Now, that was a very handy idea because if you were king, you could say the natural state of things, I'm king and you're a slave. That's the natural order of things. And that was a very powerful argument. And they said even nature's that way. The natural order of things is that this thing should stop. It's the natural order. Or that the natural order of things is down. That's the natural order. They didn't ask for why is it that way. Like, why are you king? That would have been hard. so I think I personally think that science, Galileo, and that's probably why I got into such trouble, was trying to say, ask the question why. And that's tremendously powerful. So the answer is that things change. So you think, if a thing is moving along, why should it stop? If there's nothing to stop it, why should it go forward or back or right or left, up or down? If there were nothing stopping, why? Why should it change? So Galileo said it shouldn't. If a thing is moving along, it should just keep going, unless you do something from the outside. Which is really contrary to all our experience because they were dragging carts through the mud and it seemed like you need a lot of push and pull to make a cart move. But what they forgot was that there's a lot of friction. If you get the idea that things should move by themselves, unless you mess with them, then you say, well, okay, you're pulling, but the mud is pushing you back. It's holding you up. So there's a balance of forces and there's really no net force acting as you're moving along. That's a tremendous idea. And not obvious, you see. So the same is true in circular motion. Let's see if I can do this right. Okay. It's oranges or avocados, but it's very good. So a ball will normally go in a straight line. If I want to go in a circle, as you will do a number of times in this, like in atoms, electrons going around, you have to pull it in. See, I'm pulling it in, preventing it. It wants to go in a straight line, but I'm pulling it in. And that's the type of, just generically, we say a force that pulls the thing in is called a centripetal force. So the third one, the ball going in a circle, or yeah, this second one here, the ball going in a circle, the reason it goes in a circle is that I hold on to it, but if I don't, it goes in a straight line. Now, of course, it didn't go in a quite straight line, because if it didn't go in a straight line, it's because there's another force acting on it. See, so we discover forces. If we see a thing changing its motion, we look for the cause. And the cause is some external force. The fact that ball went in a curve is an indication there's a force acting, and so we then invent the idea of gravity. We say there must be a force acting, and then we try to figure out what are the properties of this gravity force. And that's now, then we get to the idea, the interesting idea. Well, in this case, you could see that I was pulling the ball in and making it go. But what about the moon going around the Earth? Or something even more familiar to all of us, even as children, is magnets. There are forces that act without contact. For example, this guy here, I'm bringing you one magnet here and another. Did you see that? look at this guy too is responding, and I'm not touching him. See, we find that there are some forces that act without contact. And so we look for first a description of them. And the usual way is, some students have difficulty with the idea of a field. All we're trying to say by using the word field is that we think that there's something must be coming out of the magnet which is able to move. Oh, let me try that again. It's able to move this compass needle, this guy here, if you can see it, at a distance. So we think there's some emanation coming out of this. And the word we use out of the common language is field, like have a field of daisies. Well, it's a big spread of daisies. So there's a big spread of some influence coming out of these magnets. So we use the word field, and it's nothing more than trying to explain what's going on around this. Now, here's a fun thing I would do with you. Do each of you have a pencil? I'll show you another field. Why don't you hold the pencil this way, horizontally, and then loosen your grip. Now, you have determined the field that you're in, the gravity field. If you look around, you'll see the gravity field is downward. So all of you are now like, maybe like iron filings. See, because those are perhaps too strong, but you see, your pencil is now like an iron filing, but you're in a different field. This is a magnetic field. And you see how they line up as though something's coming out of the magnet? Something's coming out of the earth, which is lining up your pencil. So you're in a field, and the field is the same. We'll find pretty much the same in the first row as in the last row. That's because the earth is huge, and we're just very close to the field of the earth between the first row and the last row is the same. Although if you go very far, let's say you go thousands of miles from the earth's gravity will decrease. Just as if I pull these apart, it will decrease also, because I had to get them really close together. See, the force does change eventually, so much so that it was able to pull. So that field, the magnetic field, and the gravity field, it's not so easy for us to demonstrate the variation of the gravity field, but you know that you can get outside the Earth's gravity field if you go far enough away. And again, this idea you become weightless. That's, by the way, that's not the same reason that astronauts are weightless. That's another story which we may get into sometime. But we'll talk about it. But the point is that the idea of a field should not be very strange to you. So this is something you've seen before, probably the magnetic field. The gravity field, you just demonstrated yourselves. That's telling you the gravity field. Now, the field that we're going to be talking about today, beginning today, is the electric field. And the electric field was a little less easy to find because natural magnets were discovered thousands of years ago. There were rocks that sort of lined up with the earth, certain directions in the earth. So natural magnets are easy, but natural electrics are not so easy to come by. This one seems to be a little bit something. Maybe not. Yeah, actually, it's attracting a little bit. Yeah, but it's not as strong an effect. So electricity is seemingly much weaker than magnetism, and it was more or less of a curiosity. You could walk across a carpet and touch something, you get a little spark. I don't know if it's happened to you. Or sliding off your car seat, you touch the side of the car, and if it happens, you get a little shock. Curiosity. It's not a big thing. Magnets is really more obvious. But you can create electricity by just rubbing things together. Somehow, you can get a much bigger effect. Let's see what happens here. Again, see, I'm not touching anything. This is one of those interactions at a distance. So, look, the argument is that a body in motion should stay in motion, and it should keep going unless it's acted on by an external force. Galileo swore to it, and Newton made a law. So, there's some kind of a force that I've created here much stronger than it was before by this frictional thing. So, we study this thing. Also, it's space-dependent. In other words, out here, this thing, I don't know, it's blowing in the wind because it was repelling before. No, it's repelling even at this distance. All right, try from here. Well, you got to be careful. Well, this one wasn't charged, so. Okay, let's see. It's really going. Yeah, it's pretty strong. Nice. Yeah. All right, but if I bring it closer, you'll find that it does act more strongly. So the point is that, and it turns out, so this was repelling. On the other hand, it's possible to get things, if I rub it on this guy, that was repelling. Now let's see what this one does. So now it's attracting. So apparently there are two different types. So I can create two different types of charge. And I don't know who exactly defined this. Maybe Benjamin Franklin. He was very interested in electricity, of course. Plus and minus charges. And we have the, so again, we just invent the idea that the fact that these things influence each other, there must be something around this object, which is we call a field. And that when the thing is in the field of another, forces can act between them. Okay, I showed you the magnetic thing, and this is the static electricity. Now, I don't want you to confuse electricity and magnetism. They are somewhat related, but they're not exactly the same. One of the big differences is that I was just able to walk over to take those magnets. I didn't rub the magnet. It was just magnetic. The electric thing is weakly electric, and really, to make it electric, you have to do something to it. So that's one of the differences. The other difference is if I build up a big electric charge, you can get a shock. Whereas with what time is it going on? With magnets, I can touch. You can go to the biggest magnet in the world, put your hands on the two poles, and you won't get a shock. You don't want to, if there's electricity driving the magnet, you don't want to touch the electricity. But if the magnet, you won't get it. Nothing will happen to you. But electricity, can be rather different. One of the things that, well, let me do this. Well, this is a double header. Let me take this off. Electricity can give you shocks. But what this is doing is carrying charge up to this dome, charging up the dome. It's doing what I did with steroids. I mean, it's really collecting a lot of charge. So much so. See, I mean, if I have brought those balls together close enough, the electricity wants to jump across. I have a lot of respect for this thing. Supposedly, I can discharge it with this. If I disappear in a puff of smoke, class is canceled. No. So that's good. Now, maybe in fact, let's see. I can discharge it maybe to one of these. Okay, now the other fun thing is, of course, the thing is that it turns out that like charges repel each other. So that what this thing is bringing up negative charge to this dome. It's collecting on the dome. We'll explain how that does. Now, if I connect this to the dome, the electricity that's collecting on the outside, the charge, will go on here and sort of creep up on these paper. And because they're all negative, they will repel each other. So this is the standing, you stand here standing on end experience. They sometimes have children doing this. But, that's another interesting thing. And this is actually why we don't see many electrified things. Although that was electrified, if you turn off the source of the extra charge, the charge leaks away. Apparently, you see, the difference is that everything is made of electrical charges. As you know, atoms are made of electrical charges. There's always some a countercharge somewhere in the neighborhood. So that if you have excess charge, it will be attracted to this, let's say that's negative, there'll be some positive charges someplace nearby which can come and sort of neutralize it. But magnetism is different. Those magnets stay magnetic because typically there isn't other magnetic material nearby to come and cancel it out. So permanent magnets can remain permanent. That's a little bit complicated story, but that's basically the idea why, for example, you don't usually have the experience of walking along, touching a rock and getting a shock. You don't usually, unless you drag your feet, you know, do something like this, that frictionally generates some charge. But typically that's not what happens. You have to do something else. And if the atmosphere is particularly moist, the charges tend to neutralize quickly. So, for example, in the winter, it's more likely to get shocked because the air is drier and you it doesn't leak off so fast, so you can build up frictional charge. Okay, well, this is kind of a little bit light lesson, I think. But one thing, when you do read in this book, I want to give you this one idea, that the idea of electrical charge is a quantity. Very much, it comes in elementary units. And then we build up a large amount by collecting these units. But I do want to give you the analogy with water. Namely, water is made up of water molecules, and a quantity of water, maybe a gallon of water or a liter of water, or more accurately a mole of water, namely 10 times 10 to the 23 molecules of water, it's a quantity. The electric charge is a similar thing. It's a little elementary unit, equivalent to a molecule or an atom. And if you have a lot of them, we build up, if you have 10 to the 16th of them or so, or 10 to the 18th, in fact, you have what's called a coulomb. So a coulomb is kind of analogous to a mole. It's a number of molecules, or a number of electrons. A coulomb is a number of electrons, a very large number of electrons. So you want to be clear on what is the meaning of charge. It's a quantity of this stuff that we just created. And then we'll see later how the quantities interact with each other. Okay, I'll post some homework tonight, and we'll be due next Friday. So I hope you'll learn some more about this stuff then. Thank you.